proof by contradiction. We start off with a mathematical statement that's definitely true. So something like this. Something's even. So we can write it as 2n. So that's a true statement. That's something that would be given right at the beginning of a question. Now we're doing proof by contradiction. So we don't start off by assuming something is even. We have to do the opposite of this. We have to contradict whatever's been given. And the contradiction will be that it's odd. We're going to assume that something is odd. So I'm going to use 2n plus 1 in my working out, in the maths that I do, in the algebra that I do. I'm going to assume something is odd. So I'm going to use 2n plus 1. So I'm going against the statement here that was given. That's a true statement. This is something that I've made up that contradicts the true statement. So we do some maths and it turns out whatever was given is actually even. So my assumption of something being odd was wrong. So from the specification of the exam board, some things that you need to know for proof by contradiction include the irrationality of root 2, that root 2 is irrational. That's not limited to root 2, it could be like root 3 or root 5 and whatever else, but similar problems. And that we have an infinite number of prime numbers, and so on. Now, this is not a formal example for proof by contradiction. The actual working out for proof by contradiction is quite long, and one of the things that we might come across is what I'm about to go through now. So if a squared is a multiple of 2, so a is a multiple of 2. Well, how do we know? So let a be equal to 2n, a multiple of 2, exactly what it says here, square, factorize out the 2, so a squared is a multiple of 2. Let's try another one similar to this. If a squared is a multiple of 5, so a is a multiple of 5. Let a be equal to 5n, 5 times an integer, that's the 5 times table, so a multiple of 5. Square both sides to get a squared. Factorize out 5, which means a squared is a multiple of 5. So we've shown if a squared is a multiple of 5, then a is also a multiple of 5. That's what this bit's showing here. We can generalize this. So if a squared is a multiple of k, so a is a multiple of k. Again, how do we know? Let a be equal to kn, square both sides, factorize out a k, like so, and this is showing us that if a squared is a multiple of k, then a is also a multiple of k. Okay, so first example, proof by contradiction to show that if a and b are members of these numbers, and what we've got here are integers, positive or negative, including 0. Okay, so if a and b belong to these set of numbers, then a squared minus 4b will never be equal to 2. So this is a true statement, but we're doing proof by contradiction. We have to contradict this statement, and the way we do it is by saying that this should be equals, that a squared minus 4b equals 2. So we're going to assume that from the beginning because it contradicts the given statement. So we have this. Rearrange to make a squared the subject. Factorize out the 2. Now a squared is equal to 2 times something, and this part in the brackets is an integer because b was an integer. So we have a multiple of 2, something that's even. A squared is even. If a squared is even, that means a is even. If a squared is a multiple of 2, so a is a multiple of 2. So because a is even, we're going to let a be equal to 2 times c, where c is an integer, because 2c now represents an even number, a multiple of 2. So I'm going to substitute that a squared like this, expand the brackets, divide by 2, factorize out the 2. Because c and b are integers, c squared minus b in brackets here will also be an integer. So we have 2 times an integer, and 2 times an integer will always give a multiple of 2, which is even. But that is not an even number. I definitely know that this side is a multiple of 2. It's an even number. So it's not equal to 1. It cannot be equal to 1. Our original assumption that a squared minus 4b equals to 2 was wrong. So the statement given in the question right from the beginning was correct all along. This is what we call proof by contradiction.